Welcome to Chem Help ASAP. In this video, we'll demonstrate the synthesis of a common ligand used in inorganic chemistry, dibenzylideneacetone. We will discuss the reaction, perform the experiment, isolate the crude product, and characterize the material. Handouts for the lab procedure and NMR spectra are available through links in the video description. The synthesis of dibenzylideneacetone goes through an ALDOL condensation. This reaction is a staple in organic chemistry. It starts with a ketone and an aldehyde. The reaction is normally performed in a base, and the product is an alpha-beta unsaturated ketone. The alpha carbon in the product comes from the carbon next to the ketone in the starting material, and the beta carbon arises from the aldehyde carbon. Here is how the reaction occurs. This is not a mechanism because we are not showing electron movement. This scheme only shows the key reaction intermediates. We start with the ketone. The base deprotonates the alpha carbon of the ketone to form an enolate. The enolate performs a nucleophilic addition by attacking the electrophilic aldehyde. The resulting tetrahedral intermediate is protonated by a solvent, water, or ethanol in our reaction. This gives an initial product of a beta-hydroxy ketone. This product can again be deprotonated by base to make a new enolate. Elimination of hydroxide gives the alpha-beta unsaturated ketone. Note that each of these steps is reversible. What's interesting about aldol chemistry is that one product or intermediate may not be much more energetically stable than another. If that is the case, then why should this completely reversible pathway often give rise to a single product? Well, there are many tricks one can use to help this reaction form a product. You can use a very strong base to jumpstart the first step. Sometimes water is removed as the last step occurs to drive the equilibrium to the final product. Very often the final product is relatively insoluble in the reaction. In order to achieve equilibrium, the reaction generates more and more product, only to have the product concentration never increase, because the product continuously precipitates from the reaction solvent. Okay, so these are some of the essential ideas of aldol chemistry. Here is today's reaction. We will react a very simple ketone, acetone, with benzaldehyde in base and an ethanol water mixture. This is actually a double aldol condensation. The ketone forms an enolate on the right and does an aldol condensation with benzaldehyde to give this initial product. The other side of the ketone then repeats the reaction to get the final product. The key to the success of this reaction is the solubility of the product. The initial product that I've shown toward the bottom, it likely initially forms in the reaction as a somewhat soluble oil in the reaction. This initial product continues to react and forms a very poorly soluble, higher melting product that rapidly precipitates from the reaction mixture. The product from this reaction is dibenzylideneacetone, often called DBA. DBA is sometimes used as a ligand for complexes of transition metals. Our procedure is loosely adapted from an organic syntheses reference from the 1930s as shown at the bottom of the slide. Let's start the reaction. Well, let's start weighing out all of our materials, and we are going to weigh everything at the balance. So the first thing we're going to start with is some potassium hydroxide. These are pellets. Now I want to get about 5 grams of these pellets, and this doesn't need to be exceptionally exact, so I'm just going to tap them out. 5, that's 3.2, 4.0, that's overshot. Okay, that's overshot to 6.1 grams. Now I'm going to go ahead and keep that, but that is more than I intended. About 5.1 was what I was aiming for, but that's okay. So that's 6 grams of KOH on the balance. Remember, KOH is a pretty strong base. So we don't want to handle this with our hands or anything. But what I'm going to do, and we don't want to leave it on the bench because it will absorb moisture and ultimately CO2 from the air. So I'm going to go ahead and take this 5.1 grams in all, and right here at the balance, put it in 30 milliliters of 1-to-1 ethanol water, and I'm going to put that to the side. So that is doing its thing, ready to go, even if it is more than I intended to have. Okay, so now let's put another weighing paper on the balance. I'm going to tear that. Now I'm not going to weigh anything directly on this weighing paper, but I am going to put a Erlenmeyer flask on here. Now I put the weighing paper down because I'm going to try to weigh some liquids, and when you try to weigh liquids with a pipette over a balance, sometimes you get a stray drop, and you know there's a risk of that. So I'm going to kind of use the weighing paper as a paper towel to protect things. So the first thing we're going to add is acetone, and I have a little bit of acetone in this vial. I don't think it's critical for acetone. Let's make sure we tear, but I want to get about 1.5 grams. Now this doesn't need to be exact, but I do want to know exactly what I get, because this will ultimately be our limiting reagent. So there's a gram. We want about half of that again. Drip, drip, drip. You can't quite see this readout here, but we're doing okay. It's 1.3. Let's go slowly. 1.45. 1.47. We're getting closer to me just saying we're done. Okay, one more. That is 1.49 grams. That's fine. We just need to know exactly what that is. Okay, 1.49 grams. Now, I'm going to be a little risky because now I'm going to try to weigh out our benzaldehyde in this same Erlenmeyer flask. Now, I just want to make sure I get enough of the benzaldehyde. A little bit of excess is fine. I want about 6 grams, so I'll probably aim for 6.1, 6.2, 6.3. So let's tear this out. Here's the benzaldehyde. I have this in a vial. Benzaldehyde is kind of a finicky reagent. It tends to readily air oxidize. So we'll work with this efficiently, but again, you don't rush. Don't take unnecessary haste, because then you're going to make a mistake. So we do want to respect the stability of our benzaldehyde, but at the same time, this won't happen instantaneously. And our reaction can tolerate a little bit of air oxidation just fine. If the reaction couldn't, we would use a different means of weighing this out. Okay, that probably looks like a lot on camera. I've added a little over 5 grams. It's 5.5. Let's get this up a little bit. I said I'd maybe go to 6.2. Let's go to 6.2. We'll have a little bit of excess. That is 6.19 grams. Fantastic. Now, this is now a mixture of acetone and benzaldehyde. I'm going to go ahead and add in a mixture of ethanol and water. I'm not going to do it over the balance because that would be risky. 30 milliliters of ethanol and water, and everything is slowly dissolving. Now at least we have both of our reagents, our benzaldehyde and acetone, and our KOH is well on its way of being dissolved. Now we'll take both of these, we will take them over to the hood, and we will start our reaction. Okay, now we're in the hood, and we have our KOH solution, and I have added a stir bar to this, and I'm going to start that going. Great. And we have our solution of benzaldehyde, acetone in a mixture of ethanol and water. What I'm going to do is I'm going to transfer this solution, our benzaldehyde and acetone solution, into our KOH solution. I'm not going to do it all at once. I'm actually going to add it by pipette. And this is going to take a little bit of time, but it will allow us to sort of watch the reaction occur. So you can see that was a full squirt of a pipette. Now I'm not doing this slowly at all. This is not some, ooh, one drop at a time. I'm just squirting it in. Now, if you look at the solution, you'll see it is starting to yellow a little bit. Our final product is actually slightly yellow, so that's a good sign. It's still completely clear, at least from where I'm standing. It looks completely clear. It is not cloudy. Now, as a general rule of thumb, one of these full pipettes, this is a 9-inch pipette, one of these full pipettes holds about 2 milliliters of liquid. So I'm not getting any more than 2 milliliters of liquid per squirt. So it's going to take, 15 or more squirts. Oh, okay, there, I don't know if you were watching, but the solution, it had gotten darker and yellow, and now it's getting cloudy. So now we're forming something that is insoluble, or not very soluble, in our reaction medium. And that's a good thing, because we expect our product not to be soluble. Now, it could be the intermediate, the monoreacted material, but at least that's the first step to getting our final product. Now, unfortunately, there's not a whole lot more dramatic to see in this reaction, because once it goes cloudy, I mean, that's kind of the big finish. Now, what is happening is, even though some of the product may have formed, as we're adding more of the reagents, now more and more product will form. So this will hopefully get thicker and thicker with precipitate. And we are getting close to being done with this addition. Now, the procedure I'm following does recommend adding the benzaldehyde and acetone solution in portions. That's why I'm doing it this way. If you go on the internet, you can find other people who have done this experiment. And some people do the addition in 2 large portions. They let some of it react, and then they add the second half of it and let the rest react. Okay. Now, this solution, it may be hard to tell from the camera. I'll move the camera in a second. But it's definitely opaque with product. Now, what I'm doing off camera is I'm pouring a little bit of just ethanol, not ethanol water, but just ethanol into this beaker, just to rinse out anything that got left behind. And that little bit of ethanol is not going to mess up the proportions of our ethanol water overly, so we're fine there. So this is going. Let's pull this to the side. Now hand swirl it, and you can see when I hand swirl it, there's plenty of solid. The solid is kind of slopping up on the sides. So this reaction is going. It's rocking with the stir bar. By touch, it's maybe just a little bit warm, but I wouldn't say it's hot, but it's barely warm. Okay, this is virtually room temperature, but I would say this is a slightly exothermic reaction, and as it goes, we're generating a little bit of heat. So we'll just let this stir. Clearly it's doing something. I don't think it's probably done, but just to make sure, we'll give it a little bit more time. What's encouraging is we got a nice color change and obviously lots of product forming. So whatever it's doing, I think it's what we want. So let's give it some time to react, and then we'll come back and finish off this reaction. It's about an hour later, and here we are. This thing is super thick with solid. Bring it into view. You can see it it's more solid than liquid, it seems, which is not really true, but it regardless has a lot of solid in it. So what we're going to do is we're going to take this. There could be some solubility of the product in that liquid. So to minimize that, we won't be able to completely eliminate it, but to minimize it, let's put it on ice and let that cool. And we'll let that cool for maybe 30 minutes, and then we'll be ready to do a suction filtration using a Buchner funnel. And we'll need a pretty good sized Buchner funnel, because that's a pretty good amount of product. So that's what's coming up, a Buchner funnel filtration. Wonderful. Well, our reaction mixture should be nice and cool by now. We have a Buchner funnel. This is a pretty good sized Buchner funnel for a fairly large amount of product. And I have a little mixture of ethanol water. So remember, when we seed our filter paper, in a Buchner funnel, we want to make sure we use pretty close to whatever is our solution that we're filtering. And this is ethanol water. Now I could just use water, or I could just use ethanol, but since it's a 50-50 mixture, I'm going to actually make up my own solution and squirt this in on the filter paper with this microphone. I don't know if you pick it up, but there is, the suction is on. Let's get everything wet. Let's take the camera and look inside and see. Okay, all of our holes are covered up. That looks good. Now we are ready. Swirl this around and to do our filtration. And that is some thick material going in. So look in the bottom, all the color is coming through. Now, I'm just going to use water to rinse this out. I'm not sure that's 100% ideal. No, we know there's an impurity in here because I used excess benzaldehyde to do this reaction. So I know there's at least a little bit of benzaldehyde in there. I'm going to say this is clean enough. We've transferred enough out of there. Now I'm going to rinse this filter cake. We have plenty of base in there, so let's try to rinse that off. And benzaldehyde does have a low level of water solubility. So we'll use water to rinse out any excess base and hopefully to remove any benzaldehyde. You see there's some cloudiness there in the bottom. That's not a huge surprise. There could be some partial reaction products that are filtering through and are not completely water soluble. And as I add more and more water to this, this goes from being an ethanol water mixture to more like a water solution with a little bit of ethanol in it. So some of the impurities, maybe a little bit of our product or benzaldehyde, is now less soluble on the bottom, and that's what's causing that cloudiness. Anyway, I'm not alarmed. The procedure I'm following explicitly says that our product is virtually insoluble in water. So you can feel free to use as much water as you want to rinse off any excess base or anything else that's entrapped in that solid. So I think that looks good. Now I'm just going to take this out of the funnel. I'll spread it on a watch glass. We'll let it air dry, and we'll come back once it is dry and find out what kind of yield we have, what kind of crude yield we have on our product. Okay, well now the solid has been spread out on a watch glass. I say spread out. I really should have used a larger watch glass to give it more of a spread, but that's what I used. I under-anticipated how much solid would be formed. There's a big hole in the middle. That's where I removed the stir bar. I'm not sure how well it comes out on camera. Our product is 5.78 grams after drying. I think that's a pretty good yield. This reaction should have a very good yield. All the literature sources cite 90%, 95%. So we would expect a high yield for this reaction. I will note one thing: I haven't taken any of the characterization data for this compound yet. I'm a little curious to see what things look like, because when I was spreading the material out on the watch glass, I kind of detected a sort of a cherry smell. Cherry smell is associated with benzaldehyde, and we did have excess benzaldehyde, so I hope I got just about all of that rinsed off of the solid through the filtration. But of course, maybe I didn't, and maybe that's what I was smelling. Hopefully it wasn't a lot. The NMR will certainly tell us that, and maybe the TLC, and maybe a little bit in the melting point. But now we're off to characterization of this isolated crude product. Here is the TLC of the isolated product. This TLC was eluted with a mobile phase of 10% ethyl acetate, 90% hexane. The RF of this main spot is 0.21. This looks like just one spot, but there is a bit of a shadow down at the bottom of the plate. This crude product seems fairly clean, but it may not have a very high purity. Pristine is a word of praise that organic chemists use to describe a very pure product. This reaction product is perhaps not pristine. The melting range of the isolated product was 105 to 108 degrees Celsius, The literature value, which I took from the reference shown in the reaction slide earlier in this video, is 110 to 111. So our experimental melting range is a bit low and a bit broad. Both the TLC and melting point are consistent in that the product is probably not of very high purity. Let's see what the NMR indicates. Here is the full NMR spectrum. I always like to show the full spectrum, though the signals for our product are restricted to a narrow part of the spectrum. This spectrum was performed at 400 megahertz. The solvent is DMSO. These upfield signals, one for water and the other for DMSO, are these two peaks. Let's now zoom into just the signals from our product. Here we go. I did not do us any favors with the integration values. This molecule should have 14 hydrogens total, but our integrations only add up to about 7. The scale for the integration values is off by a factor of 2, so our integrations should all be doubled. 2, 6, 6. This upfield signal, a nice wide doublet, is 2 hydrogens, and likely corresponds to the 2 hydrogens alpha to the carbonyl. The most downfield signal is likely a mix of multiple overlapping signals, a multiplet. This signal consists of the other alkene hydrogens, the beta hydrogens, and probably these 4 orthohydrogens on the aromatic ring. That is a total of 6 hydrogens. The remaining hydrogens are all under the multiplet in the middle of the spectrum. This multiplet includes both the meta and para hydrogens on each ring. There is not much to interpret in this spectrum because so many of the hydrogens overlap. Regardless, all the hydrogens are present and have a reasonable chemical shift. I say reasonable, but these alkene hydrogens are a bit further downfield than one might expect. Normally, I look for alkene hydrogens in the 5 to 6 ppm range. These are pulled downfield because of conjugation with both the carbonyl and the aromatic rings. I will also highlight the baseline of the spectrum. There are some bumps in the baseline. They're not terrible, but this sample does include some impurities. This is a crude product after all. We only filtered it. We did not do a proper purification. Regardless, although it is not pristine, the spectrum looks fairly nice. Let's now calculate the percent yield. We used 1.49 grams of acetone. It has a molecular weight of 58.08 grams per mole. That comes out to 25.7 millimoles of acetone. We used 6.19 grams of benzaldehyde. Benzaldehyde has a molecular weight of 106.12 grams per mole. That is 58.3 millimoles. Remember that the stoichiometry of the reaction calls for 2 equivalents of benzaldehyde relative to acetone. If we think of acetone as being 1 equivalent, then we actually used 2.27 equivalents of benzaldehyde. We used more benzaldehyde than the reaction required, so benzaldehyde is present in excess. A slight excess, but still in excess. Acetone is therefore our limiting reagent, and our theoretical yield is 25.7 millimoles. Note that I'm skipping KOH in these calculations since it is a catalyst and does not come into our yield calculation. Let's now focus on the product. We obtained 5.78 grams of product with a molecular weight of 234.29 grams per mole. We therefore got 24.7 millimoles of product as our actual yield. Our percent yield is actual divided by theoretical times 100 for a 96% yield. Wow, 96. That is incredible, but it's not that incredible. Keep in mind, we have some impurities in this product. Those impurities add some mass and inflate our yield. Regardless, this reaction is still definitely high yielding, and the product obtained is fairly clean. I hope you enjoyed seeing this example of an aldol condensation and preparation of dibenzylideneacetone. Remember that procedure handouts and copies of the NMR spectra are linked through the video description. Please subscribe, like, or leave a comment. Take care.